Let's understand electromagnetic induction in this video. Have you ever wondered how a power plant makes electricity by spinning coils and magnets? Or why a moving magnet makes a meter needle flicker? This idea is called electromagnetic induction, and it turns motion or changing magnetic fields into electric current. Long ago, Faraday and Henry showed that a moving magnet near a coil makes a current appear in the coil. In one simple experiment, Faraday pushed a bar magnet towards a coil connected to a galvanometer, and the pointer moved only while the magnet moved. When the magnet was still, the pointer stayed at zero, so motion mattered, or more precisely, the change did. In another setup, he used a current-carrying coil instead of a magnet, and moved this coil near the first one. And again, the galvanometer showed a brief deflection. A third test showed no motion was needed if the magnetic field through a coil changed. For example, by switching a battery on and off in a nearby coil. So the common point is this: a changing magnetic flux through a loop makes an EMF which can drive current. Now, what is magnetic flux? Think of it as the number of magnetic field lines going straight through a loop. If the field strength is B, and the loop area is A, and the field makes an angle theta with the normal, then the flux equals B times A times cosine theta. If the field is perpendicular to the loop, the flux is largest. And if the loop plane is parallel to the field, the flux is zero. Faraday summed this up in a law that we use all the time in JEE problems. He said the induced EMF equals negative the time rate of change of magnetic flux. And the negative sign is Lenz Law, which tells the direction. In words, Lenz's law says the induced EMF opposes the change that made it, so it protects energy conservation. For a circuit with resistance R, the induced current equals the EMF divided by R. Let's solve a numerical example together to make this concrete. Example number 1. A coil of area 2 square meters sits in a magnetic field that is decreasing at 10 Tesla per second, and the coil resistance is 5 ohms. The magnetic flux is phi equals B times A. So the magnitude of induced EMF equals A times absolute value of dB by dt. Substitute values. EMF magnitude equals 2 times 10, that is 20 volts. Current magnitude equals EMF divided by resistance. So current equals 20 divided by 5, which gives 4 amperes. By Lenz's law, the field was decreasing. So the induced current tries to increase the inward flux. Therefore, the current is anti-clockwise. Example number 2. The flux phi 2 equals 7t squared minus 4t in Weber. Resistance is 20 ohms. Find current at t equals 0.25 seconds. First find d phi by dt. That is, d phi by dt equals 14t minus 4. At t equals 0.25, d phi by dt equals 14 times 0.25 minus 4, which is 3.5 minus 4 equals minus 0.5 Webers per second. The induced EMF equals negative d phi by dt. So EMF magnitude equals 0.5 volts. Current equals EMF divided by resistance. So current equals 0.5 divided by 20, which is 0.025 amperes or 25 milliampere. One more quick example. A conductor length 0.4 meters moves at 7 meters per second across a field of 0.9 Tesla. The induced EMF is BLV. Substitute and multiply to get 0.9 times 0.4 times 7 equals 2.52 volts. So what do we learn from this? We learn that any change in magnetic flux through a loop gives an EMF, that the formula links flux to BA cosine theta, and Lenz law. Let us quickly remember, flux changes when B, A, or the orientation changes, and induced current equals EMF divided by resistance. Electromagnetic induction led to generators, transformers, and many technologies we use every day. Keep exploring these ideas with practice problems. They reward careful steps and clear signs. Thanks for listening. Stay curious and try more examples on EduRev to strengthen your skills. There is no rush, just steady practice.